JJ, welcome back. We are here with ASUS once more, and for this video, our third video, we're going to look at the Windows side of your software story, and how that ties into what you guys are doing on Haswell, what's new, and how that really builds upon some of the UEFI innovations that we talked about in the last video.
Yeah, that's definitely right. I think for us, though, we view it as a combination of being hardware and software.
Okay.
Because, of course, the execution of everything we're doing, it's very deeply ingrained within not only the coding aspect that we have within the UEFI, but that we are using as best as we can the hardware that we have in place in the system as well. And even some of our auto-calibration technologies are specific to the hardware that you have installed on your system, however that might be and whatever it might be.
Yeah, so you can't just take this this software suite that you guys have here and run it on any platform. Like it depends on the hooks that you guys have on the board itself.
That's one aspect, but even aspects such as our automated overclocking technology is cooler specific and even DRAM specific. So we always try to give you a result that's really going to be specific to your platform and even vary. Take, for instance, the system that we're going to demonstrate here would have actually one result in our Northern California offices because it's actually a bit cooler than it is here in your home. So you're going to have a bit of difference in terms of the result that we're going to be representing because of the variance in the temperatures.
Interesting. So your well, let's get to it, and then I'll ask you the questions here. So what are we looking at?
So first off, before we get into our four-way optimization, which is a big it's a big feature point on our Z87 series of motherboards that feature DIP4 or dual intelligent processors, is AI Suite 3. So this has kind of been our consolidated all-in-one system utility. So this allows you to pretty much overclock your system. It allows you to make modifications towards efficiency with the EPU component. It allows you to do full real-time adjustment to the VRM section of the board, as well as even advanced fan calibration options. So we've pretty much reskinned the entire interface to hopefully allow it for it to be even easier to look at and work with, add some more persistent information, as well as even add some cool usability elements to it. So that's where we're going to jump through first.
Okay, take me through it.
So here we can see that we've got the primary kind of HUD or layout that we have, and this is pretty much representative of key data that would occur after we run the four-way optimization. So as you can see right here, we have such items like CPU performance. The fan expert 2 would let us know which fans have been benchmarked and what would be the corresponding fan curves if we highlight over them. Optimizations that may have been made to the VRM and how the phase switching and things like that might occur. And even for the EPU component, where we might maybe optimize undervolting to the CPU when the system's under an idle or an away state, what's going to be the reduction that you're going to have in terms of the amount of wattage that's not being taken up in terms of the CPU.
So folks who aren't familiar, can you explain quickly what EPU is?
So EPU and TPU are part of our DIP4, our dual intelligent processors. So they're hardware ICs that we have on the motherboard that work in conjunction with the system as a whole to be able to allow us to maximize, let's say, energy efficiency or performance tuning aspects and hardware and monitoring aspects. So we can see right here, also down in this bottom section, we have an entire new level of kind of persistent data ranging from CPU frequency, DRAM, core voltages, temperatures, and fan speeds. One note that we do want to go ahead and touch on though quickly here is for the CPU temperature. There's always some people that wonder about how our temperature information is different than other third-party programs, and this is because the temperature that we present is a polled value from a thermoresistor that we put underneath the CPU socket and is read in conjunction with the DTS data, and then an offset is created from the TCAS. It's also part of the DTS reading information that you have. So it's more of a weighted representation of what your real system temperature is, as opposed to just the more average temperature that you're getting from DTS data.
Interesting. So how does that work? You're measuring temperature basically underneath the CPU in the socket.
Correct.
And you're also reading the temperature. The CPU has its own on-diathermal sensor.
Correct.
And what do you do to those two values?
So we essentially kind of average those two values, and
okay.
we create an offset also to take off the TCAS, and then from there we kind of present you that more kind of weighted temperature. So there's going to be a little bit of differences if you compare that to just running a third-party utility that's only reading to DTS values, and that we feel represents a more kind of realistic of what your system-specific CPU temperature is.
So you're really trying to approximate the temperature on the top of the CPU then by doing this. Okay.
So from there, we go ahead and we can jump in, of course, to some other sections that we've gone ahead and made some changes on. So if we go ahead and go into our CPU frequency, so let me go ahead and get out of here and go into this primary section, you can see that we still give you all the standard things you would expect, such as BCLK adjustment, multiplier, we can do group tuning, we can adjust the cache ratio, which is a new item for this generation. But one of the things that we're really happy about introducing is manual entry. So we can go ahead and we can key in specific voltages. So let's say if I went to manual here, I could go ahead and key in 1.2. And that's a bit of a change from the previous generation where you would only have the option to be able to just do a slider. So you have a bit more granularity about how you want to define your voltages, whether it's going to be with the slider or whether it's going to be through manual key in. Now, one of the other cool things is that we're kind of thinking about always trying to make things easier for the user. So you can see that we've color-coded the voltage scales, because a lot of times users can come into the platform without really being knowledgeable about where safe ranges are. And so, of course, now that it's color mapped, it allows you to easily know where those safe or maybe those more moderate or more extreme voltage tables might be.
Gotcha. And then that CPU cache ratio, that is controlling the speed of the last level cache.
Yes. It's kind of tied into previous generation for people to be aware of, kind of like the uncore.
Yeah.
And it manipulates also sometimes the achievable CPU frequency. So depending on that frequency, you can sometimes go ahead and push up other frequency points. And we'll touch a bit more on that in some of the manual overclocking aspects. So we can see that we have all that information weighted in here, and that still maintains. Then, of course, the CPU strap, which is new for this platform, same as what it would be on X79, just gives us more memory divider support. For EPU, we've added some really cool functions in here as well. So you're going to see them in terms of this add-on USB controller power as well as add-on SATA power. So we have the ability to go ahead and have the system auto-calibrate, detect what's being read there, and when it's no longer in an active state or in an away mode, it can essentially power down those additional controllers, which is independent of the devices themselves being shut down. So it gives us a little bit more power management flexibility, helps to reduce a little bit of the power being consumed by the system.
So what happens when those controllers go into their disabled state? They look like they've been physically removed as far as Windows is concerned.
Correct.
So when there's a wake event, Windows redetects
it re-triggers them back on and they come back on, correct.
Gotcha. Now, is that a feature that was added from user feedback, or is that you guys just trying to push the envelope?
It's just us trying to be able to extend the functionality. There's always users that are kind of asking us, how can we keep fine-tuning aspects of control in the system. And even some of the options that we've incorporated are sometimes just about making them easier to get to than they might be within the Windows operating system. So an example of that is if we just switch back to our high performance section, you can see the monitor off and sleep. Those options you already have in power management within Windows, but they're just more easy to access right here as opposed to diving into a couple of layers to get into them.
Okay.
So the last portion we're going to see right here is configured max CPU power. Our previous generation, we had package profile targets of 45 watts or 35 watts. For this generation, we can actually manually set it to whatever you'd like, and the system, the software and the hardware combination will automatically make adjustments to the voltage as well as to the CPU frequency to go ahead and allow you to fit within that package power profile.
Gotcha. So like we said last time, this allows you to kind of have almost an infinitely configurable TDP.
Pretty much, yep. Of course, we continue to have all the full real-time VRM options, so things like load line calibration, which for this generation has actually very little impact due to the IVR being in place. But you still can control things like OCP, the phase ramping policy, and things along those lines, and those are all the same options you would have as if you were in the UEFI, but they're being completed real-time. And the last one, of course, is Fan Expert 2, which is our advanced software. Allows you to do per head control of either 3-pin or 4-pin fans. We can do things such as doing smart gradients in terms of our fan curves, fixed mode for RPMs. We can even adjust the spin up and the spin down times, which are pretty much the aggressiveness between each one of those points, which helps to create a quieter fan ramp experience as opposed to, let's say, it be very coarse where it might be very abrupt when it ramps up or down. So a lot of granularity there. So with that, we're going to now touch on the for optimization aspect. So this is something that we feel adds a lot of cool value to when you're going to be taking your system for the first time and trying to figure out how do I maximize its performance. So at this point, what this utility is pretty much going to do is when we enter in, it will take our auto tuning technology, our Fan Expert technology, the EPU, and the power management technology that's offered for the VRM and execute them all in one click. The main differential as opposed to, let's say, fixed preset value is going to be that this is going to be system specific, CPU specific, DRAM specific, cooling specific. Everything that's being executed is specific to your system and even the environment that you're in. If you take it from one area to another area and you rerun it and the ambient temperatures were different, then you're going to have different results.
Interesting. So it is to a certain degree looking at how hot the environment is, and it's in fact in using that to impact what maximum overclock it thinks that you can get. Correct.
And as part of this platform, we've also tried to have it be sensible in terms of the way that we define your overclock. We're still trying to give you enhanced performance while doing it in a safe, effective, and efficient way. So we're only going to utilize an adaptive vid versus a manual-based vid, and we're even going to cap that adaptive vid so that even though there could be the potential of getting better results by going to higher voltages, we're going to cap that at a result so that we always feel confident in terms of the amount of voltage that's being supplied to your system
Okay.
is never over a safe value.
So what is that? How do you determine what the max bit is? Is it a percentage that you don't want to go over?
In terms of, for us, in terms of what we've defined, that's come through the course of testing, you know, almost now 600 CPUs at this standpoint,
Okay.
testing to see where tolerances are at, what thermals get created based off of those tolerances, and
Interesting.
things along those lines.
So you characterize 600 chips, and then you feed that you data mine that basically.
Pretty
and
much.
that's how you determine this.
And that's where we've kind of create the voltage level that we won't exceed.
Gotcha. Now, do you guys update that application, that end of the application, right? So presumably you don't stop at testing 600, right?
Correct.
As new steppings and as the process matures.
Yes, we will actually, as updates can come out, if we continue to see variants introduced in the marketplace from maybe newer steppings, then that would be factored into the development of the application.
Gotcha. So if you go ahead and hit start on this, it's going to come out and it's going to pick an overclocked setting. How far off of the true max overclock will that setting be?
In our testing, actually, it's pretty close to, I'd say, 85 to 95%.
Okay.
So in optimal cooling conditions, I can tell you for this system right here, we're going to effectively get to about the best of what it would be able to do under an air-cooled configuration. So if, let's say, the CPU could do 48, I would say in most situations, based on that 48 would probably take a little bit higher voltage, this is probably going to give us somewhere about 46 to 47.
So you're talking about multipliers, so 4.6 to 4.7 gigahertz.
Yeah, so it's going to get it pretty close to the way of what you would actually be able to do, but probably in a safer way that most users wouldn't generally approach, because most users tend to overclock with a manual-based FID.
Yeah.
The other differential, of course, in our process is going to be that we're consolidating a huge amount of time that normally the end user themselves doesn't have knowledge about, right? Because anybody that's new to a platform, it takes you a certain amount of time to kind of get up to speed, understand where safe voltages are, temperatures are at, and everything kind of along with those lines. So we have two options under the auto tuning. We're going to just default to the ratio only option and go to the extreme tuning, which is going to be the real-time auto tuning process. But if we did want to go ahead and have our system be specifically ramped up utilizing the BCLK, we would have that option to go ahead and execute on that. So we're going to go ahead and set the TPU, the EPU, the fan, and we're going to go ahead and let it run through its process.
Okay, so we've had a reboot now. What's going on here? What are we looking at?
So we're pretty much looking at an initial result that the CPU's been given, which is 4.3 gigahertz.
Okay.
So this is kind of like a baseline profile that we've gone ahead and through that research with those CPUs, we've gone ahead and said that we know the CPUs are going to be capable of this. We've set it to that, and now it's going to go ahead and attempt to dynamically scale up specific to our system.
Okay.
So at this point, you can see I've gone ahead and opened up the task manager, because one of the next steps you're going to see is that we have an integrated system utility that will run actually a stress test. Now, one of the changes that we made also based on the previous generation, and that we've incorporated this generation, is we have per core tuning that comes into effect. So we do have the ability to go ahead and have, let's say, 1 and 2 cores be set to a different multiplier ratio versus, let's say, 3, 4 cores, or all cores being active.
Okay.
So we can see right here that it's going through the full core stress test, so we can see at the same time that the CPU utilization is now fully peaking out. Once it goes ahead and passes that initial stability test, it'll then go ahead and go to the next portion and continue bumping it up. And this is very similar to the same way that a manual user would go about overclocking their system. They would make adjustments to the ratio, they would make adjustments to the voltage, and then they would go ahead and stress test their system. When they find out point of instability, then of course they would restart and keep going after that process until they get to a point that they're satisfied with.
Gotcha. So I see now it's gone off to a 2-core stress.
Correct.
Okay.
And so we're going to go ahead and continue to escalate the frequency as well as on the voltage until we get to our maximum result. Once it's completed the auto tuning process, it'll go ahead and switch over to the next portion of the 4-way optimization, which would be the EPU, or the undervolting process, and then from there next over to the fan expert, which would vary depending on how many fans you might have set up in your system. And then lastly, the VRM management actually occurs at the same time that the TPU adjustments are occurring, because of course those are just making switches or changes to things like OCP or phase management based on the frequencies that we're setting. So those are tied into like our auto rules to maintain best performance and stability.
So interesting. So it's going to first find out how fast you can run the chip. Then it's going to find out how low of a voltage you can actually run it at those speeds at.
That actually occurs at the same time. So the EPU proponent is more so when dealing at idle, at idle base voltages. So we can maybe even tune that down a little bit, because part of the advantage that we're working with being an adaptive VID is we're going to get that nice drop in CPU voltage when the VRD comes down in terms of the non-turbo ratios.
This is determining the overclock voltages, and then the EPU portion will determine kind of the idle voltages.
Yeah.
Gotcha. And then after that, it's going to try and run the fans as low as possible. possible.
Yes, it will actually fully calibrate all the fans. The baseline profile that will be set would be our standard profiles, which would be a good compromise in terms of acoustics to also cooling for your system. But all the fan-specific data, such as its maximum fan curve, would be kept in by the application. So if you then went in and you clicked on silent, all the fans would all turn off. If you went to full speed, it would know exactly what the maximum speed is. So it's taking all that calibrated data and just allowing you to then have the most flexibility at how you want to define the characteristics for your thermal response in your system.
Okay.
So at this point, you can see that it's gone ahead and continued, and we're now at 4.6, and you can see that now it's actually reached a point of instability. It knows this. The application is even modified to allow us to have a quicker reboot and play. So from here, it'll go ahead and continue through its process until we have the final result.
Interesting. And how many times on average does this have to happen?
It would entirely depend based on your cooling solution. But for us, if you pushed it to the top end cooling solution to be on the market, similar to what we have right here, which is a dual radiator, closed loop liquid cooling solution, or like an actual dedicated water cooling solution, you'd probably not be looking at more than, I'd say, 10 to 12 minutes.
Okay.
With, of course, more basic cooling solution, you could be looking as maybe as little as 3 to 4 minutes.
Okay.
So we'll pop back over to the desktop. Of course, the application will go through, and we'll let it complete, and we'll come back to it once it finishes.
Okay, so we've gone through the overclocking. It's picked 4.6 gigahertz. What is that for? Is that for how many cores?
That's actually 4.6 on 2 cores, and then 4.5 across all cores.
Okay.
So we've gone ahead and completed our overclock. We can see the information that's given us about the EPU and how it's been able to modify that. The fan curve information, which we go ahead and see per each one of the headers. So that's all great. So here quickly, we're just going to show you one other point of consideration as to how we're actually overclocking the system. Now, we made a point earlier that we're doing the overclocking through an adaptive vid policy, which is an option that we've actually had on our boards for a couple of generations, but some people might be new to it. Pretty much this just means that we're being able to keep the ability to have the voltage drop down when the CPU frequency is up. This allows us to go ahead and keep the best overall voltage efficiency and also help to maintain the best overall power consumption, even for an overclock based system. So we're just going to go ahead and open up a system monitoring utility like Ada to take a look at the frequency and see what the voltage corresponds to. Now keep in mind that for this generation on this platform, if you decide you want to go ahead and pursue additional stress testing through, let's say, a third-party application, whether it's something like Prime 95 or OCCT, Lynx, any of those applications like that, you're going to have to be prepared for a change and what could occur when you load up that application after you've stress tested this. Now, this version of the software is not final, but there will be an actual advisory message that would let you know that if you want to proceed system testing like this, we actually do advise that you consider this as a baseline for your system and then pursue to use a manual vid, as you won't see this abrupt voltage change that we're about to demonstrate here. So we're just going to go ahead and open up Cinebench as an application to reference as putting some load on the CPU. And in most situations, it's actually going to probably be much higher load than you would normally do with your system day in and out, whether it's going to be gaming or web browsing or general productivity. So we'll go ahead and just select all cores to be utilized. And we'll run that. And we can see right here that our CPU voltage isn't exceeding 1.30 volts. Mm-hmm. So we're all well and good. That's great. There's no issues there. We're able to maintain that thermally dissipated with our current cooling solution. And the next step, though, we're going to do is we're actually going to open up Ada's system stability test. And this system stability test actually utilizes a heavy number of instruction sets that are on the CPU and produces a certain instruction set that the CPU will respond to differently.
And the key here is that what you're basically saying is if you look at traditional applications and a lot of what people run today, they aren't heavy, AVX
Correct.
workloads that are really going to stress, honestly, some of the most power hungry parts of the CPU, which are like, these big, SIMD floating point units now. And that gives you that max VID at overclock that we just saw there. But if you shift to a workload that is very AVX heavy, that is pushing, the most power hungry units on the chip will actually even exceed that maximum voltage.
Correct. And even the voltage that's been defined, and whether you do this manually or whether it's through our auto-tuning application as part of the 4-way optimization, this will occur regardless. So there is no way for you to stop this short of you using a manual vid.
Okay.
But you're not going to have that total power efficiency, that reduced idle and idle voltage footprint, as well as reduced even thermal footprint, because you're no longer providing a same consistent static voltage. So just to show you a representation of this, we're going to go ahead and fully load it, and you can see right there our voltage has jumped now all the way up to 1.355. So it's something you would have to be conscientious about. Under normal workloads, you wouldn't necessarily need to worry about this, and even under stringent workloads that are even utilizing AVX. So it is really, for us, we've only internally seen this within stress test applications, even complex programs that utilize it like Blender and Premiere, and a lot of other programs where you have instruction set support and you could persistently be utilizing the CPU utilization. Don't produce this. So this is more so for you guys that are interested at stress testing your CPU.
Gotcha. So it's kind of like that power virus scenario where Intel is manually forcing up that maximum voltage.
Correct.
Interesting.
Okay, so from here, I'd say let's jump into manual overclocking.
Okay, so we've kind of given you a little teaser of some of the stuff you have to deal with Haswell overclocking. But JJ, now you're gonna, given your experience, 600 plus CPUs now that you guys have collectively
we're gonna
tested.
get into the nitty and gritty.
Okay, let's do that. And for that, we're gonna use a different board. We've been using one of your Deluxe board now.
Correct. From here, we're gonna jump over to our actual Maximus 6 Extreme.
Okay, so we've switched motherboards and we're on an ROG board, and now you're gonna help us understand some of the ins and outs of overclocking Haswell.
Correct. So we've gone ahead and entered into the UEFI. So this is going to be focused for users that are a bit more comfortable in the advanced environment of the UEFI and looking to kind of maximize their manual overclocking of Haswell or 4th gen CPUs. So what I'm going to try to provide is a little bit of insight to specific functions, and secondary to that, certain kind of, let's say, baselines that you can attempt to go ahead and define to see if you can pursue certain level overclocks.
Okay.
So first and foremost, we would go ahead and go into the AI overclock tuner section. And we're going to go ahead and just enable XMP because in most situations you're going to probably be using XMP memory. The first thing though we do want to keep in mind at this point is going to be that the DRAM divider support for this platform, while at stock frequencies is very good, tends to go ahead and drop down in its ability to sustain that DRAM divider as we increase the CPU frequency. So that's going to be in respect to that if right now, let's say our current CPU frequency is 3.5, right, and we want to shoot for 46, it's going to be considerably more difficult to run 46 with 2800 as far as being the memory divider versus, let's say, 4.6 with 1333.
Okay, so it becomes a balance, right? It's more difficult to get both high memory and high CPU overclocks at the same time. So do you recommend backing off on the DRAM overclock and prioritizing CPU first?
100%. If if you're going to be more patient, you're going to want to pursue asynchronous overclocking first. Mm-hmm. So first and foremost, if you have an XMP enabled kit, just go ahead and enable the profile, see if you can actually comfortably post boot and run it at that frequency without any issues. And then from there, once you validated that, feel free to go ahead and pursue an asynchronous or a pursuit of just the CPU multiplier being increased and finding out what your maximum is. And then from there, you can attempt to go ahead and do both.
Gotcha. So you're saying make sure XMP works.
Correct.
Reboot with stock CPU frequency.
Yep.
Reboot, make sure that works. Once that works, then back off of that entirely?
Yes.
Okay.
Yes. We'd 100% would recommend that. And the main reason being is, as we've seen within the CPUs, their variance is that we have CPUs that can hit 46 at 1600 with 4 DIMM, but even going up to, let's say, 2133, the CPU could be failing in terms of stability tests. Okay. So you don't want to essentially compromise your overclock based on just being a little bit too overzealous on both sides.
Gotcha.
So we're going to go ahead and go down from there, and most of the other values we won't need to adjust. In reality, while this platform is allowing us to have more granularity with BCLK frequency adjustment, as well as offering a CPU strap, in most situations it's going to probably be easiest in terms of overclocking through the pursuit of an adjustment to the multiplier or the ratio. Now, what you can keep in mind is that with this platform being a bit more sensitive to the DRAM dividers, especially as we increase the CPU frequency, you can go ahead and consider an adjustment to the BCLK as a way that you might be able to maximize some of the margin that could be left on your memory. So of course, if let's say you have 2133 and you notice that when you set the 2133 with your corresponding overclock and it's too high, you can only comfortably run it in 1866 memory divider, maybe you can go ahead and bump up the BCLK just a little bit to maximize a little bit more performance, getting closer towards the 2133 without jumping all the way to the 2133 divider.
Okay.
So that's just for the guys that are interested in just eking out a little bit more performance than what they might be running with from default. So the next step here is we're going to, of course, go to the core ratios, and our initial basic pursuit is going to be something like 46. Our expectation is the majority of the CPUs at launch should be somewhat within this range, probably closer to about a 45x multiplier, with good quality CPUs definitely getting to 46, and great quality CPUs being between 46 to 48, with some variation on the memory divider that's being supported. Now, the interesting thing with this platform is that there's the introduction, of course, of that ring bus at play, and that can influence the primary CPU frequency. So what you can do is, if let's say you've gone ahead and defined 46, and 46 is able to be achieved with stability difficulty and you want to pursue going to the next stepping, so let's say 47, but you notice even with the incremental voltage increase, you're still not able to stabilize that. What you can do is you can adjust the cache ratio, as we're calling it, and you can drop that down. So if, let's say, once again, we were at 46, that was fully stable, but we wanted to get to 47, and even with a couple of steps of voltage, what we think would stabilize it, we're not getting it, we can go ahead and define this at, let's say, 45. The disadvantage of this is that ideally you want to run the cache ratio with parity at the same frequency as your primary CPU ratio. That's going to give you the best performance.
And is that the default mode?
Default mode, there is no default mode inherent because we've actually created our own auto rules to allow you to maximize the overclocking potential.
Okay.
So in most situations, you actually wouldn't even need to adjust this value.
Okay.
But for users that sometimes maybe don't want to use our auto rules or want to maximize the absolute best performance, you can go ahead and attempt to force a 1-to-1. Now, we don't default force a 1-to-1 just because it's actually going to be only the outstanding best grade of CPUs are going to be able to hold the same cache ratio as the primary CPU ratio. So even some CPUs may be able to hit 46 will require, let's say, the ratio running significantly lower than 46, while other CPUs may be able to run everything in unison.
Okay. What should users expect to see?
In most situations, we're probably going to say that once you get to that 46 bracket, you will probably need to adjust this range. Now, we want to make one note that in most situations, you want to stay within a range of about 100 to 300 megahertz. As dropping more and more than that, of course, you're going to keep dropping the performance, but core is still king at the end of the day, so of course you'd rather have 48 running at 45 with the cache ratio versus running 46 parity.
So is that what is that roughly the delta that you're expecting most folks to see, where they run their cores at 4.6 gigahertz and their last level cache runs at like 4.3?
It could actually even be less than that. I mean, we found actually the most success with it being even lower than that. Actually closer to probably, I'd say, about 39 to 40.
Okay.
In terms of really ensuring that you can have that frequency be ramped up upon. And like I said, it's going to pretty much just keep dropping down further in terms of percentage-wise as you try to maintain a closer 1-to-1 parity between the primary ratios and then the cache ratios.
And what's the benefit in setting both a min and a max CPU cache ratio? Why not set just the max?
Well, they're linked together in terms that the minimum cannot be less than what the maximum is associated with. So these actually need to be running the same value. You can't be underneath. So they need to be paired.
Okay.
Yeah. So we're just going to go back to 46 here, and like I said, we can go ahead and keep these set to auto. And the board will allow it to kind of do its work. Some people that were familiar previously with PLL over voltage, this is actually already inherently built into the architecture for the CPU. We've left it there as a flag that can be forced, but we found overall that there's no value to being modified, only in very, very rare situations. So if for some reason you even make an adjustment to the cache ratio and you're still not finding an improvement, you could go ahead and attempt to enable it. So moving past that, we're going to go ahead and jump all the way down to our voltage tables. Now for this platform, there are 3 different voltages you could utilize: a manual vid, an offset vid, and an adaptive. Really the main ones that we're going to focus in on are going to be a manual vid. This is probably what majority of enthusiasts are most comfortable with, as far as just easily kind of working with a voltage, knowing what the voltage is going to run at idle or at load. It's not the most efficient. For the most efficient, we are going to want to go ahead and use an adaptive vid. It's a little bit more complicated because we have to monitor the offset that occurs as the VRD increases voltages as we increase our multipliers, but it's going to provide you the benefit of giving you the best total efficiency and helping to reduce some idle temperatures as well as your idle power consumption.
Now, can you take folks through the difference between adaptive and offset? Because both are kind of an offset.
Yes. So if we go back to an original offset, the main issue that we're going to have here is that you're still going to get the drop down in voltage, but as we increase the offset is still going to occur at the base voltage that's being supplied to CPU, even at the base ratios. So the let's say, increased turbo ratios. If we go ahead and we jump up into the adaptive vid will not touch the base voltages that are being supplied to the CPU. It's only going to modify let's say, modified turbo voltages.
Gotcha.
So that's where we have a difference. Ultimately, there's probably no reason for you to run an offset versus an adaptive. Adaptive inherently has all the benefits of an offset, but because the architecture allows for it, we've maintained all 3, so we can allow the users to go ahead and ultimately define what they'd like.
Yep.
We're going to go ahead and just stay with a manual to make it easy. And I would recommend a baseline value of 1.2. If your CPU can hit 4.6 at 1.2, you've got a very capable CPU. If not, you're going to want to increase in moderate voltage values. So you could go ahead and go to 1.25, 1.250, and excuse me, lastly, you could go ahead and attempt 1.275. Now keep in mind that if you're going to be running stress tests, you'll have thermal considerations that you have to keep in mind. So with a voltage such as 1.275, when you run that stress test application, you're going to essentially be almost thermally limited by using generally like a single stage radiator. So something in the class of like a Corsair H80 or like a 920, something along those lines. If you're going to be running a stress test with that voltage table, you're going to be almost near the point or at the point of throttling. So you just need to be conscientious that if you're going to be going at greater voltages than this to be able to go ahead and reach stability or even posting of your CPU frequency, then you're going to make sure, you need to make sure to have essentially a thermal solution in place that's going to be adequately being able to cool that. Now, of course, if you're under a gaming load, then your temperature is going to be considerably lower, even at the bracket point of 1.25 to 1.275. Under most, I'd say, under most application loads, you're going to probably be looking somewhere between about maybe mid 60s to maybe low 70s. Of course, that's going to be dependent on your ambient temperature.
Now, what are the default core voltages that come on the parts that you've seen?
So your default voltage is going to be, I believe, approximately 1.050.
Okay.
And then your load voltage is it's not too much higher than about 1.1. So it's fairly low. So your jumps up that you have are not going to necessarily be a huge upswing from the baseline voltage that you have running, but you're going to have a fairly finite kind of value room to be able to play within, depending on the thermal solution that you're going to be utilizing.
So my old rule of thumb was, I always kind of wanted to stay in that 10 to 15% overvolt range. Mm-hmm. It sounds like with Haswell that's not going to give us enough. Yeah,
I would say that only the best quality CPUs are going to be comfortable hitting that type of margin. So I think that realistically, if your goal is to try to be targeting somewhere between 45 to 46, or even greater than that, as we've noted, your voltage range could be quite large. We've seen 46 capable CPUs as little as 1.050, and we've seen some require as much as 1.4 volts. So it's a pretty big wide swing to account for. Hence why, like I recommended, if you could do 4.6 at 1.2, that means you got a pretty good CPU. It's maybe not the best, and up to about 1.275 is kind of an area for you to play around with.
Okay.
So from there, we're just going to drop down to probably two last ones that may give you some granularity or flexibility at maybe improving the DRAM divider support as you increase the CPU frequency. So the CPU analog I/O voltages right here that you have available to you. If you kind of want to think of them, it's kind of like VCCSA and VCCIO, not exactly the same, but it's in kind of a similar wavelength. So making adjustments to these can sometimes help to improve the DRAM divider that you're attempting to run. Now, there's not really a advised voltage that you should be utilizing. It's more so that actually characteristically some CPUs like one voltage and other CPUs like another.
Interesting.
So what you're going to actually want to attempt to pursue would be something, if we go ahead and drop back down here and we go to our voltages as we were in a manual mode, and you could try something like 1.150, and you would want to keep those actually parity. You want to keep them the same generally, but you could also try all the way up to 1.2. Now keep in mind once again that greater isn't better. It's just a question that some CPUs specifically like one input voltage versus another input voltage. So you just may need to try a couple of those options and see if it helps to stabilize the actual DRAM divider that you're attempting to pursue. Now, once again, we go back over and we'll reset everything back to defaults, and we'll try a different value to allow you to see that the board actually has a very good set of auto rules in place. So in most of these situations, you do not need to do these, but if you want to try to maximize, let's say, your tuning parameters and ensure that this is being what's defined on the board, then these are the reason why we're going through some of these options.
Okay.
So at this point, we'd essentially already completed everything we needed to do. So we're just going to go ahead and reload everything back to defaults and shoot for, let's say, best case scenario if you have absolutely great quality cooling and a great CPU and a great kit of memory. So we're just going to load XMP profile. We're going to go ahead and set a 48 CPU ratio. We're then going to go ahead and drop down to here as far as our voltage. We're going to choose 1.275 because we've got a pretty nice quality CPU in play. And we'll go ahead and even actually improve the memory divider a bit, and we'll jump up to 2933. We're using 2800 kits of memory. And if you notice, we didn't make any modifications to anything else.
And no modifications to even in DRAM voltage.
Correct. For DRAM voltage, the board even has an auto-negotiate table to help to compensate for improvements that are needed in that regard.
Okay.
So from there, we're just going to go ahead and reboot and see if the board reposts. So the thing that you guys want to keep in mind as you go through these overclocking pursuits is that we've seen very consistently if the board is generally able to pass the post stage and then the boot stage with the voltage that you've gone ahead and defined in, so our example was 4.6 at 1.2, should generally be pretty close to the level of stability that needs to occur. The only other thing to maybe keep in mind is going to be things like LLC for this generation, which generally aren't going to be required because, of course, the LLC is no longer in the control of the motherboard. It's now being placed on the IBR.
Okay.
Okay, so you can see we've gone ahead and actually rebooted here into the UEFI, and we successfully have gone ahead and hit 4.8 gigahertz along with 2800 for DRAM. Now, we had previously set 2933, but actually this is a brand new kit I'd never tried before. Generally, the 2800 kits have a little bit extra margin, but these ones actually didn't have the extra margin. So we went ahead and just cleared CMOS, reset back to our same defined values of the 48 with just the core voltage adjusted. We let the auto rules take place. We applied XMP, and we were good to go.
Okay.
So overall, that gives you guys a little bit of perspective on overclocking. Here's a little quick note for you guys that are going to go ahead and attempt to pursue this. You can see right here, best of luck and happy overclocking from ASUS and Anantech. Plus, we got a little bit of some quick notes for you guys to recap on what we discussed about.
Awesome, thank you. And I guess you're going to stick around for one more video. And,
yes. And
in that last video, we're gonna build a mini ITX system.
A very cool mini ITX system.
That's awesome. So stay tuned for that.